In 1989, a major earthquake strikes Northern California. 67 people are killed and damage is widespread. In 1980, Mount St. Helens, a long dormant volcano, suddenly comes to life, spewing tons of smoke, ash, and debris across the Pacific Northwest. In many places around the world, layers of the Earth's crust have been raised into towering mountains. Seemingly unrelated, earthquakes, volcanoes, and mountains have a common cause and serve as a reminder that our planet is constantly changing. When you look at a globe of the Earth, it is easy to think that our planet has always looked this way, that the continents and ocean basins are where they've always been and where they will always be. But if you examine the globe more closely, you may notice something curious. Some of the continents appear as if they may have been joined at one time. A good example of this are the coastlines of South America and Africa. When you compare them, you will find, with just a little bit of adjustment, that they match quite nicely, like pieces of a jigsaw puzzle. And see how the island of Madagascar slides next to Africa. The same goes for North America. Its eastern coastline fits nicely around portions of Africa. People have been noticing these kinds of shoreline similarities for a long time. In the early 1900s, German scientist Alfred Wegener believed that in the distant past, later determined to be about 200 million years ago, the continents had been joined in a single supercontinent Wegener called Pangaea, and then had split apart, moving ever so slowly around the globe until they reached their present-day positions. Wegener called his theory of moving continents Continental drift, and he offered additional evidence in an attempt to prove his point. Wegener found fossils of nearly identical animals in both South America and Africa. Wegener believed the only way identical animals could be found on distant continents were if the continents had been joined at one time. Wegener also found plant fossils in cold Arctic regions where these plants could not grow today. Wegener believed the plants had grown there before the continents had drifted. Wegener was convinced the continents had drifted. The only problem, he could hardly convince anyone else. Other scientists needed more proof, and that wouldn't come until years later when scientists mapped the ocean floor. What they discovered was an underwater mountain range that resembled a scar running down the middle of the Atlantic Ocean and circling the entire globe. The formation was called a mid-ocean ridge. When scientists sent an exploratory submarine to investigate the area, they discovered newly formed lava formations. Lava comes from the Earth's interior, and when it cools, it hardens into rock, as it is doing here. Rock like this forms the ocean floor. Scientists believe the only way for the lava to have gotten here was through a crack in the ocean floor. On later dives, scientists discovered underwater geysers which were being heated by magma, as well as a variety of strange life forms, like these worms, that live nowhere else. These creatures couldn't exist here if it weren't for magma heating the normally ice-cold water. So not only had scientists discovered an underwater mountain range, but a crack as well. What scientists discovered next was puzzling. The ocean floor was progressively older the greater the distance from the crack. This was difficult to explain until scientists came up with a solution. It's a solution these students are about to demonstrate. This sheet of paper represents the seafloor beneath the Atlantic Ocean. The space between the table represents the crack in the ocean floor, the mid-ocean ridge. The numbers represent the age of the ocean floor at various distances from the mid-ocean ridge. The lower numbers represent older material. As the paper is spread apart, more paper emerges from the crack. As you continue, you can see how the lower numbers are spread farther and farther apart. This is the way scientists explained how it was that material farther away from the crack could be older than material found near the crack itself. This process is called seafloor spreading.
Remember how all these numbers were all even with all of these?
If the seafloor were spreading, it would certainly explain how it was that North America could be drifting away from Africa. But this was only half the story. The other half came in the form of a children's game. We've all played Connect the Dots. In it, dots appear to have little meaning until they are connected. Then a picture emerges. Scientists were faced with their own game of Connect the Dots. But the dots they had to connect were the locations of recent worldwide earthquakes. Many earthquakes occurred on or near the mid-ocean ridge. But others occurred far from the mid-ocean ridge. What about these dots? Together, all the dots seem to form patterns. When the dots were connected, a dramatic picture emerged. The dots seemed to form sections. The Earth was not only cracked, but it appeared to be cracked in pieces. Scientists called these pieces tectonic plates. When scientists realized the Earth was broken into plates, they finally had enough evidence to explain how it was that continents could move. The theory that explains plate movement is called plate tectonics. To understand more about plate tectonics and continental drift, we have to look deep inside the Earth. The Earth's interior consists of several different layers. The inner core, which is believed to be solid iron and which is very hot. The outer core, which is believed to consist of rocky material so hot and under such great pressure that it is in a liquid state. The mantle, which is not as hot as the outer core and not as liquid. The mantle's outermost portion is solid. This is the solid outer portion of the mantle. Above this is the outermost layer of the Earth, the crust. Together, the crust and solid outer portion of the mantle form the Earth's outer shell. They are referred to as the lithosphere. It's not always easy to see the Earth's crust. It's covered by vegetation and the oceans. But if you could drain the Earth's oceans and strip away our planet's vegetation, the Earth might look something like this. Now we can see the Earth's hard outer shell. And if you look closely, you can also see the shell is cracked. The red glowing lines mark the places where the Earth's shell is cracked into tectonic plates. Each plate carries a continent or an ocean basin, or sometimes both. The plates are moving at an average rate of 1 to 2 inches a year in a variety of directions, carrying continents and ocean basins with them. Here's why the plates are moving. Scientists believe material in the mantle is circulating much as it is doing here. The movement may be caused by heat within the mantle. You can get an idea of how heat can cause a circulating movement by watching rice as it boils. What you see happening within this beaker is similar to what's happening within the Earth's mantle. As mantle material moves, perhaps only inches a year, it causes the plates above it to move as well. In some places, plates are moving in opposite directions. They are moving apart. The area where two plates are moving apart is called a divergent boundary. In other places, plates are colliding. The area where two plates are colliding is called a convergent boundary. And in other places, plates slide past each other. This area is called a transform boundary. This is a cross-section of a divergent boundary, the mid-ocean ridge, located beneath the Atlantic Ocean. The North American plate is on the left, and the Eurasian plate is on the right. Scientists believe that as the plates move apart, mantle material called magma rises to fill the gap. Magma is the name we give lava before it erupts from volcanoes, as it is doing here. The magma cools and hardens on the ocean floor, adding new crust to old. And as the seafloor spreads, North America moves farther away from Asia. The highlighted area on this globe shows where magma is surfacing between plate boundaries beneath the oceans, creating a mid-ocean ridge that circles the Earth. The ocean floor spreads in one direction on one side of the ridge and in the opposite direction on the other. The mid-ocean ridge is where plate material is created. And this is where plate material is destroyed, a convergent boundary. In this cross-section, the plate on the right is carrying an ocean basin and is moving in this direction. The plate on the left is carrying a continent and is moving in the opposite direction. The plate carrying the ocean basin is heavier and is diving beneath the plate carrying the continent. The leading edge of the diving plate is consumed back into the Earth's mantle. When one plate dives beneath another, it is called subduction, and the area where it occurs is called a subduction zone. Subduction may resemble what is happening on this lava lake, as sections of hardened crust dive beneath other sections. The highlighted areas on this globe mark convergent boundaries. Subduction is occurring at most of them. These are the areas where plate material is destroyed. Here again are divergent boundaries, where plate material is being created. Again, most of them are beneath the oceans, creating a mid-ocean ridge that circles the globe. We've already seen how plate boundaries coincide with earthquakes. Here's how earthquakes occur. The grinding of plates has been going on for so long that most of the Earth's crust is filled with cracks, not unlike the way this rock is filled with cracks. Scientists refer to a crack in the Earth's crust as a fault, and it is in these faults that earthquakes originate. One side of the fault tries to move in one direction. The other side of the fault tries to move in a different direction, but the two sides are locked in place. They can't move until enough stress builds up to move them. If you were to bend a stick slowly, you would find that it won't break until sufficient stress builds up.
Oh my gosh. Oh, wow. Look at that.
And that's what happens deep underground. The fault will remain locked until enough stress builds up, and then it will suddenly release. One side of the fault sliding past the other with a tremendous burst of energy. The energy released is in the form of seismic waves, which radiate or move outward. If you've ever thrown a stone into a pond, you've seen waves move outward in all directions. the waves in this pond are similar to the waves of an earthquake. If the disturbance is big enough, the waves will eventually reach the surface, where they can cause considerable surface movement. Earthquakes occur near divergent boundaries, convergent boundaries, as well as the third type of boundary, a transform boundary. The Loma Prieta earthquake in 1989 occurred near a transform boundary. The fault that is associated with this boundary is over 500 miles long and slices its way past several major cities. It is among the most active faults in the world. Earthquakes occur along the fault with frightening regularity. We've seen how earthquakes occur near plate boundaries. The same is true for volcanoes. These symbols mark the locations of active volcanoes. Most of them occur near plate boundaries, and some of them form a circular pattern when connected. This region of the world is referred to as the Ring of Fire, and it includes some of the world's most destructive volcanoes. Most volcanoes occur near subduction zones. As one plate dives beneath the other, tremendous heat and pressure are created, causing solid rock to liquefy into magma. The magma rises in large globs into the plate carrying the continent. Eventually, the magma stops rising. Some of the globs may form a magma chamber. As more and more magma adds to the chamber, pressures build. Some of the magma finds its way to the surface, where it can erupt, spewing forth lava, gas, volcanic ash, and debris. The eruption of Mount St. Helens in Washington State in 1980 occurred in much this same way. In a matter of seconds, much of Mount St. Helens was blown away, the mountain literally losing its top. 62 people were killed, and forest and animal life were decimated. Some volcanoes occur far from plate boundaries. The Hawaiian Islands are thousands of miles from the nearest plate boundary, yet this area is among the most volcanically active areas in the world. Scientists believe a hot spot exists in the Earth's mantle below Hawaii. Hot spots are areas where magma has found its way up through the Earth's crust, emerging on the ocean floor, where it becomes hardened by the cold ocean water. More magma follows, adding to the formation of an underwater volcanic dome. The dome becomes larger and larger and may, after thousands of years, rise above sea level. Every island in the Hawaiian chain, as well as many others around the world, were formed in just this way. Hotspots are stationary. The one beneath Hawaii has existed here for over 70 million years. But as we have seen, the Earth's plates are not stationary. As this plate moves, it carries the newly formed island with it. As the magma continues to rise, it will build another dome all over. Seldom do hotspot volcanoes erupt with the explosive force of volcanoes like Mount St. Helens. But what they lack in explosive impact, they make up for in showy displays. Lava fountains are typical of these kinds of volcanoes. Lava can shoot hundreds of feet into the sky for days on end. Lava rushes downhill in rivers. Sometimes the lava reaches the ocean. Steam explosions are common as the hot lava comes in contact with the ocean. As the lava hardens into rock, new shorelines form under clouds of hissing steam. Like volcanoes and earthquakes, mountains are the result of plate movement. This map shows the great mountain ranges of the world. Most are located near convergent boundaries. Here's how some of the world's highest mountains are made. In this example, the plate on the left is carrying a continent and is moving in this direction. The plate on the right is also carrying a continent but is moving in the opposite direction. They are colliding. Since both plates are of similar weight, neither plate dives beneath the other. Instead, they squeeze up against each other. Under the incredible pressure, layers of the Earth's surface are compressed and folded, rising high into the air. These raised layers of Earth are what we call mountains. You can make your own folded mountains simply by squeezing the ends of some towels together. The Earth's crust will fold just as these towels. The world's highest mountains, the Himalayas, were made in much the same way. They were formed when the plate carrying India collided with the Eurasian plate. Over millions of years, the Earth's crust was squeezed into folds more than 5 miles high. Today, the Himalayas are growing even higher as the plate carrying India continues to push against the Eurasian plate. Many of the world's highest mountains were made in much the same way. It's hard to see the folds because the mountains have been worn into jagged peaks by the effects of water, wind, and ice. But if you look closely, you can see how rock has been folded under the great stresses caused by moving plates. This outline gives you an idea of what these mountains may have looked like when they were much younger. Mountains are the highest places on Earth, so it's remarkable what you can sometimes find there. Fossils of sea life can be found in just about every mountain range in the world. The fossils got there when layers of the Earth's crust were thrust into the air. In this program, we've seen how the Earth's continents were once part of a single supercontinent called Pangaea. And that about 200 million years ago, this supercontinent broke up into separate continents and, moving several inches a year, reached their present-day positions. We've seen how the Earth's shell is composed of more than a dozen plates which move in a variety of directions, carrying continents and ocean basins with them. We've seen that there are 3 types of plate boundaries: divergent boundaries, convergent boundaries, and transform boundaries. We've seen that most divergent boundaries occur under the ocean, where magma rises to fill the gap left by diverging plates. The ridge created by rising magma is known as a mid-ocean ridge. A mid-ocean ridge circles the planet, and it is an area where plate material is created. We've seen that some convergent boundaries are areas where plate material is destroyed, as one plate dives or subducts beneath another. We've seen that folded mountains are made where 2 plates carrying continents collide head-on. Finally, we've seen how plate boundaries coincide with the occurrence of earthquakes, volcanoes, and some of the world's highest mountain ranges. When you look at a globe today, you are looking at a moment in time. While we can't see it, the continents continue to move farther and farther apart. About 100 million years from now, the continents will stop moving apart. They will then change directions, coming together once again. 250 million years from now, the world may look something like this. The continents once again forming a supercontinent. It will be a world much different from the one we know. Ocean waves will break upon new shorelines. Towering mountains will rise in places that are now flat. And earthquakes and volcanoes will continue to shape the new land.